All right, let's dive right in. Today, we're going inside the engine room of modern AI. We're going to look at the single most important component that allows models like GPT to actually understand language, the transformer layer.
So, it all really starts with one big question. When you type a sentence, how does a machine not just see a bunch of words, but actually grasp that whole intricate web of connections between them? You know, the grammar, the context, the real meaning? That is exactly what we're going to unpack.
Okay, so before we get into the nitty-gritty, we need to zoom out a little and see where this transformer layer fits in. It's not the very beginning of the process, but trust me, it's where all the magic really happens.
So, any text you give an AI model goes on a journey that looks something like this. It starts as raw text, gets broken into smaller pieces called tokens, and those are turned into numbers or embeddings. But our focus, it's right here, on step 4, the transformer layers. This is where those simple numbers get processed into a deep understanding. So, let's imagine our input is a simple sentence like, "The cat sat." By the time it gets here, it's not made of words anymore. Nope, it's a sequence of vectors, these embeddings we just mentioned. Each vector holds the basic kind of dictionary-like meaning of its token. This is the raw material our layer is going to work with.
And now for the main event. This next part is the most critical component of the entire layer. It's the real secret sauce, multi-head self-attention. I know, it's a mouthful, but the idea behind it is actually pretty elegant. It's all about how these tokens talk to each other. At its core, self-attention lets every single token in the sentence look at every other token, all at the same time. This is a huge deal. Older models had to read word by word, but here it's like everyone in the sentence gets to see everyone else instantly. So to make this a bit more intuitive, just imagine each token is asking a simple question. The token for sat, for example, is thinking, okay, to understand what I mean here, who else in this sentence is most important to me? Is it cat or is it the? The self-attention mechanism is what does the math to figure out the answer, creating these attention scores that link words together based on how relevant they are to each other.
But here's the really cool part. The model doesn't just ask this question once. It does it multiple times, all in parallel. And that's where the multi-head part comes from. You can think of it like having a panel of experts all looking at the same sentence. Each expert, or head, has its own specialty and is looking for a totally different kind of connection.
So what are these different perspectives? Well, one head might be the grammar nerd, figuring out that cat is the subject doing the action of sat. Another head might be the semantics expert, connecting cat and sat based on the fact that sitting is something cats do. And a third head could be looking at the bigger picture, the broader context. By doing all of this at once, the model gets this incredibly rich, multifaceted understanding of the sentence.
Okay, so the model has used attention to gather all this juicy contextual information. Now what? Well, it needs to actually process and integrate what it just learned. And that brings us to the next phase inside the layer.
The first thing that happens here is just so clever. The model takes the brand new output from the attention step and adds the original input right back to it. This is called a residual connection, and it basically acts like a shortcut. Its job is absolutely crucial. It makes sure that as the model learns all this complex new context, it never ever forgets the original meaning of each word. Immediately after that addition, the data goes through something called layer normalization. You can think of this as a quick cleanup step. It just kind of tidies up the numbers and keeps them in a nice, stable range. This is super important because it stops the calculations from spiraling out of control and makes the whole model way easier and more reliable to train.
All right, now that the new contextual info is mixed in and stabilized, each token's vector gets passed to its own little personal neural network. This is the feed-forward network. Think of it as a refining station, where each token, now fully aware of its context, gets processed on its own to deepen its meaning. It's like the model is taking a moment to think a little harder about each specific token.
And what happens right after that feed-forward network? You probably guessed it. We repeat the exact same stabilization process all over again. We add another one of those residual connection shortcuts to preserve the information from before, and then we follow it up with another round of layer normalization. This pattern of process, then stabilize, is really a core part of the transformer's design. So, after all of that, what have we actually accomplished? What's the big payoff? Let's take a look at the final output of the layer and see what's really been transformed.
And here it is, the result of that whole journey. On the left, we had our input embeddings. They knew what cat meant in a dictionary, sure, but now, look at the right. The output embeddings are just packed with context. The vector for cat now knows its relationship to sat. It's no longer just a word hanging out by itself, it's an active player in the sentence.
So why does all this complexity matter so much? Well, because this architecture is what lets models understand things like nuance and long-range connections in text. It's how they capture really complex ideas, and because they process everything at once, it's incredibly efficient. This is the engine of modern natural language understanding.
And you have to remember, a model like GPT isn't just one of these layers. It's a massive stack of them, dozens, sometimes over 100, each one feeding its smarter output to the next layer, building an even deeper and more sophisticated understanding of the text. This whole block is like the fundamental Lego brick of modern AI.
So, we've seen how the data flows and gets enriched inside a single layer. But that brings up an even bigger question, right? How does a model learn to use this whole architecture to actually predict the next word and generate text that makes sense? We're going to explore exactly that in our next explainer.